half integral, which is an integral over, let us say, a vector potential for the electromagnetic field and a complex field, which will be like now as P phi star, times an action e to the I time t. Now this action consists of one term which is minus 1/4 f square, which is the electromagnetic term. Then there is a term which couples the scalar field with the electromagnetic field. What we are assuming is that we first integrate out this quantity over phi and phi star, and what you get is an effective action which you write as e to the I integral d4x, the minus 1/4 f square action of the electromagnetism plus an L effect. And we have an expression for L effective. L effective in the Lorentz spacetime happens to be minus I integral 0 to infinity ds over x and the trace in some x space. Essentially, we reduce the quantum field theory problem to a quantum mechanical problem in 4 dimensions for some operator h which will act as a Hamiltonian, and this is the propagator to go from x to x prime, and after which we are putting x prime is equal to x, and then the L effective is given by this formula. Normally I would have written this as I by 2, but it's actually I because we have integrated over phi and phi star. So each one of them will give you a determinant factor, but that is just a question of numerical factor. So let us look at this conceptual part once again. We did this long back, so because it is long back you might have forgotten it. You originally had a field theoretic Lagrangian. We reduce it down to a hypothetical particle which is moving in 4 space dimensions, if I have been doing Euclidean thing, or 1 time and 3 space dimensions which are given by this xi. Then you introduce a 5th time parameter which is s. So for a moment again imagine that we are doing Euclidean. If we are doing Euclidean, the time and space doesn't have any difference. So you have 4 space dimensions and you think of this s as a time dimension. Then I can think of a Schrodinger equation in 4 space dimensions and 1 time dimension, determined by this Hamiltonian h. Okay, and this gives you the evolution, or rather the propagation kernel, and the effective Lagrangian is given by this integral. This is what we have. Now in this particular case, this Hamiltonian h is what we wanted to sort out. This h in general is given by, for a general electromagnetic action here, is given by minus I del minus QE the whole square plus m square. So let us just check the signs. You should always have a e to the minus is m square because that is there even in a free particle. So this m square should come with a positive sign. Then if q is not there, this is going to give me a minus del square. So along with it, this will give you a plus del square. So the Hamiltonian operator will become box plus m square. Box plus m square is correct in our signature because box has a minus normal del square, which will give you a plus k square. So plus k square and plus m square should always go together because k square plus m square will give you the energy. Okay. So this is what you have as far as the h is concerned. Now up to this point, everything is completely general. You take an arbitrary electromagnetic field. Suppose you think of this A as an arbitrary function of x, and suppose you solve this problem. Well, then you will become very famous because that means you would have solved Schrodinger equation for an arbitrary potential. Because this is like a Schrodinger Hamiltonian, and essentially this A is an arbitrary potential in t, x, y, z in 4 dimensions. In fact, you have solved Schrodinger equation for an arbitrary potential in 4 dimensions, 4 spatial dimensions. Okay, so that cannot be done. So in order to compute this, you have to resort to some kind of an approximation. So the approximation which we are going to use is physically well defined. What we are going to say is that we are integrating out the fast modes now, which are made of the complex scalar field. So the vector potential AI is supposed to vary slowly. So we will take the assumption that we are going to think in terms of a constant electric and magnetic fields. Therefore, AI is going to be linear in Xi. So if you Taylor expand AI in terms of Xi, the lowest order term will have a coefficient which is Fik. Then you will have derivatives of the Fik appearing. So since Fik is not supposed to vary too rapidly, you are just stopping that. So this corresponds to a constant electric and magnetic. Then we said that we can simplify this quite a bit. Because if you have a generic electric and magnetic
So this, that part, can you please repeat again?
Sorry, which part?
Before, about
what I said now. Okay, so remember that the philosophy behind this approximation is that you always have some fast modes and slow modes, and you integrate out the fast mode. Here the fast modes are given by the scalar field phi and phi dagger, which I have integrated out. The slow modes are the AI. So what do I mean by slow? If I say AI is a constant, it doesn't make sense because AI is not a gauge invariant object. But I can say that Fik is constant, that is the electric and magnetic fields are constant in space and time. That is what we are saying. Okay? So if I take Fik to be a constant and then plug it in and we want to evaluate it, it turns out that that problem can be reduced to the only problem we know how to solve, harmonic oscillator. Okay? So in that sense it is a nice idea. So this is what we have. Now I have a constant E and a constant B in space. And for a generic case, I can always choose the Lorentz prime in such a way that E and B are parallel. So we took it along the y-axis, if I remember right. So then we chose our AI to be minus EY 0, 0, minus BZ. Okay, let me just make sure that is the notation which I have used. Yeah, that is fine. Yeah. Okay. So you can check with your notes as well that this is what we have used yesterday. So you will take this kind of a vector potential and we plug it into this and we reduce this Hamiltonian into a tractable form. Alright. So the place where yesterday there was a sign error is because the square of this is a 4-dimensional square. So the time part of this should come with a plus sign and the space part should come with minus sign. I forgot to put that in because I was thinking I was doing Euclid. So here we have minus I dt minus q times this quantity, which is plus q e y the whole square. That is the first term. Then I have this minus.
Sir,
Yeah.
AI should be Bx.
Bx. Okay. Sorry. Is that what I did last time?
Yes.
Okay. Fine. Okay. Yeah. The Z component should be x in order to get you a curve. Okay. So we have the zeroth component of this, which will come with a positive square. With this minus sign, it will be negative. Then I want to take the special components. These two special components, A does not contribute. So I should have this overall minus sign. Then I square will give you another minus sign. Then I will have this del square here with a minus sign. So it is plus dx square plus dy square. This is the part where we want to make sure that the signs are correct. What I am saying is that there is an overall minus sign here. Let's forget about that. Then this square itself will give me a minus sign because I am spatial things and I am taking a signature which is plus minus minus minus. So there will be one minus sign from this. Then this I square will give you another minus sign. So that is positive. But there is an overall minus sign. Okay, that is exactly what we have here. So this is minus d square by dx square. Then I have the last term, which again will be plus because there is a minus here and there is an overall minus sign coming from the signature. And inside it is I dz plus qbx the whole square. M square really doesn't matter, but we will carry it along. Okay, this is your Hamiltonian. Now let us look at it for a minute. This thing depends on y and depends on x. So when I am taking this kind of a product, I can't do anything about y and x. I have to deal with it by actually calculating the kernel. However, it is independent of two other coordinates, namely t and z. So there I can use my standard momentum representation. Therefore, I can write this quantity as minus I integral 0 to infinity ds over s, and in evaluating this trace, I can now introduce dp, the time component, and a dp dz component, which are ignorable coordinates, 2 pi the whole square, and here I only need to put the transverse coordinates, which are x and y. X transpose e to the minus is h x transpose, and replacing this my I dt by minus p0. Actually, whether I put minus here or plus doesn't matter, because we are integrating over all p0 from minus infinity plus infinity. But this is just to use the standard convention, and this I will replace by p. Okay. So let me again make sure that is what we have. Minus p naught, and the other one. These two things should have a difference in sign. Yeah, this is correct. Okay, so this is what we have. This will differ by a sign from what we did yesterday, because that overall minus sign I missed yesterday. Okay. Now it is somewhat plain sailing. What we do is that I take this QE outside here. So this gives me minus q square e square. This divided by QE. And here I take the QB out. And I get plus q square b square. Then I am going to call this whole quantity as something. Okay? So let me call this L2. So I define this quantity here. L1 as this quantity x plus pz divided by qb, and L2 is y minus p2 upon qb. So if I do that, this becomes L2 square these derivatives become derivatives with respect to L1 and L2. Do you remember whether it was plus or minus? Yes, that seems to be minus. Minus d square with respect to L1 minus d square with respect to L2. Okay. Then I have this quantity, which becomes q square plus q square v square L1 square. This is roughly where we stopped yesterday, plus m square. Okay. So what have we got here? So we have here a Hamiltonian whose path integral kernel we need to compute. Now that Hamiltonian first has a constant term, which we don't care. I can just put that m square here and take a e to the minus is m square outside all the way up to this. This is independent of P naught and Pz. P naught and Pz are now inside L1 and L2. Okay? So the remaining terms let us look at. So if I look at the terms with L1, I have a minus L1 square plus this quantity. So let us combine, let me write this as L2 and this as L1, and think of this as plus here and put a bracket here, and take this and put a bracket here. So m square we know how to handle. Let us look at this term and this term. This is minus d square by some d L1 square plus q square b square L1 square. This is harmonic oscillator. It is minus del square plus a potential. So the parameters of this harmonic oscillator is that the mass of the oscillator, because there will be a del square, there will be p square by 2m. So there will be a 2m in the denominator, that is becoming 1. So the mass is equal to half. So the mass is half in the units which we are working with. So this quantity is supposed to be half mass times the omega of the oscillator square times this L1 square. That quantity is turning out to be q square b square. But m is half. So this is 1/4. So this is into 4. That means the frequency of the oscillator here is, the frequency is 2 times modulus of Q. The frequency is supposed to be a positive number, so you have to put a modulus of QB. See, B could be in this direction or this direction, or charge could be negative, etc. But so I will not write it all the time, but hereafter, wherever there are expressions like QB and QE, you should know that it is actually given by modulus sign. So let me write that also down here. The frequency of the oscillator is 2 QB for this case. Now if you look at this case, this has the same operator as this, but there is an overall minus sign. So that means it's an inverted oscillator. So the potential is now going to be like in one direction like a saddle point, and in the other direction is your standard harmonic oscillator potential. Okay. Now where did this sign difference come from? Because it is going to carry through all over the calculation and lead to very important physical differences between electric and magnetic field, which I explained to you the other day. That electric field will produce particles. It will lead to an imaginary part to the effective action. Magnetic field will not. This extra sign difference came from the fact that our signature had a difference. So it is deeply connected with the way Lorentz transformation symmetries of the space-time work, and that is what distinguishes electric and magnetic fields. Okay, it came from that expanding this quantity with a plus sign for the zeroth terms and the minus sign for the spatial term, and the zeroth term is the one which had the electric field in this case, and this is what is happening. Okay. Now we are almost done. What we now have to write down is this quantity. So that I am going to just quote the result, because you guys know how to write the harmonic oscillator kernel, and you take the coincidence limit of the harmonic oscillator kernel, and then normally the harmonic oscillator kernel's coincidence limit would be written with x1, x2 and a time coordinate t. Here the time coordinate happens to be s. Okay. So if you do that, you will find that the harmonic oscillator kernel has the form. Let me first write it down and then we will check whether the expression is correct. It is m omega over 2 pi I sine omega times the time coordinate whole to the power half exponential. I think it is minus pi m omega square, the coordinate whatever it is, x square tan omega t by 2. Let me just check that. M omega 2 pi sin omega t exponential I m omega x square tan omega t by 2. Okay, m omega x square and there is no sign. Fine. So this is what you have. So just to remind you, what you are supposed to do is to go back to what Gangal has taught you in path integrals. Take the expression for the path integral kernel for the harmonic oscillator. That will have an x1 and x2. Put x1 equals x, x2 equals x. So one term will go away and the remaining term will have a sine on the inside and a cosine outside, and that will give you tan. Okay, this is what you will get. So this you do it as an exercise. So in this particular case, we know that m is equal to half. So that makes this 4. Omega is going to be either QB or QA. So let us do it for, let us say QB. So this is QB. And T happens to be S. That is because when you do the kernel, you go from one point to another point in a time interval capital T. The capital T there was the kernel to go from x1 to x1 0 to x2 capital T. Here we are talking about a time interval which is S. So in order to substitute into this, you should put S here. Then again m is going to be half. Oh, this is wrong. Omega was 2 QB, so it is sine 2 QB less, and this is 2 QB. So omega is going to be 2 QB, so this goes away, QB, and x here corresponds to this L1, so this is L1, QB, yes. This is what you
L1
square. Okay. So are you with me up to this point? Okay. Now if you want to do this, you have to take this part, you get that. Then if you take this, you will get the one for the electric field. But the only difference is that omega becomes I omega. Okay. So when omega becomes I omega, you have an I factor here and here. This will just become sin x. Then here when you work this through, there will be an I factor here and an I factor here. So that will just change the sign to minus. Okay. I won't even write it down. So you get exactly the same expression for that. So you just put in both the expressions here. And the propagation in the x direction and propagation in y direction are independent. So you just get a product of these two. Then you are supposed to integrate this over dp0 and dpz. That is trivial because p0 and pz integrals will be essentially the same as qb times dl1 and qb times dl2. It is like an integration over L1 and L2. So let us see what will happen. I mean, I am going to write down the final answer, but let me orient you towards what you should expect. You are going to integrate this over L1. So if you, this is a Gaussian integral with an L1, so you will get square root of pi divided by this object. Okay? So you will get in the denominator square root of tan of this quantity. That will be square root of sine and a square root of cos on the top. This is sine of twice that quantity, so that will be 2 times sine and a cos of the half, and therefore the cosines are going to go away and you will get the 2 factors of sine. So essentially you are going to get 1 upon sine this QBS in one case and sin h QBS in the other case. Okay, this is what will happen. So everything is taken care of and you only have this extra integral which is left here. Okay. So now let me write down that final expression. after you do all these integrals, you get it to be L effective this is minus integral 0 to infinity ds upon s cubed, which is exactly the kind of form which we had. Okay, there is also a 4 pi square. 1 over 16 pi square. ds upon s cubed e to the minus I m square s. That comes from just this m all the way going for a right, e to the minus m square s. Then you have two factors which are QES from the electric field divided by sin h QES. Then you will get a factor which comes from the magnetic field, which will be QBS divided by sine this is what we have. At this stage, now that the calculation is over, you can quietly replace E and B by A and B, because we argued that there are two quantities, A square minus B square is, we introduced two quantities by the definition. Just to remind you, A square minus B square was E square minus B square, and AB is equal to E dot B. And we said the final answer can depend only on A and B, and in the gauge and Lorentz prime we have chosen E is equal to A and B is equal to small b. Okay, so you can, in this particular gauge, you can replace it by A and B, and since the result has to be gauge invariant, this is the final result. Now, first of all, I want you to appreciate the result. What we have done is to do a path integral over a complex scalar field in the presence of a constant electromagnetic field, and you want to know how it affects the electromagnetic Lagrangian. What is the electromagnetic Lagrangian? It is half of E square minus B square. The correction to that is this, okay, which depends on E and B in a very complicated manner. And if you go and write it in terms of A and B, you know that the A part is going to give you something which is, it is a function of E square minus B square, and it is a very complicated function of E square minus B square, and it is also going to now involve E dot B, okay, which original Lagrangian did not have. So it's a highly nonlinear correction to the E square minus B square Lagrangian, which is obtained by testing. And the analysis is, compared to what we have got, the analysis is trivial. It just involves using harmonic oscillators. Okay, so it's a very nice result. Originally due to Heisenberg and Euler, not the mathematician Euler. He was long since dead when Heisenberg was born. This is the Heisenberg student with that name, and later on done very nicely by Schwinger. Okay, so this result goes to Schwinger. Okay, now we want to, rest of it is just to extract physics out of this. That is what we are doing. First of all, we want to look at its real and imaginary parts. The way it is written, it is not even clear it will have an imaginary part, etc. But you see that there are poles lurking all over the place. Okay, and these are the ones which are going to give you the imaginary parts. In order to understand that, you have to recall that whenever we are doing an integral over something like S, there is an I epsilon prescription, which tells you that the integral which we should be computing has to go slightly below this axis. That is, if this is your real S, this is like a time coordinate, and this is your imaginary S. Again, this is a very old result. It comes from the fact that we are thinking of IS being equal to S Euclidean, or S being equal to minus IS Euclidean. And this comes from taking S Euclidean e to the minus I part. Okay, e to the minus minus I pi by 2, and e to the minus I pi by 2 comes from taking e to the minus I epsilon and rotating. E to the minus I epsilon, when you do a Taylor series, it is 1 into minus I epsilon, and we are essentially integrating only on the positive s here, 0 here, so we only need this one. So this is the way we are integrating. So first thing it tells you is that any poles you have on the real axis of the s is immaterial. Okay, so those poles are contributed by the sign factor, which tells you that the magnetic field is harmless. The poles coming from the magnetic field are not going to do anything because we are going below those poles. Okay, but by the same token, in order to get that integral well defined, because we have to get the top integral well defined, that means I had to make this Is equals Sc, which is equivalent to rotating to this. Fine. Now assume for a minute that we have rotated it. Then what will I get? That is easy to write. Because when you do that, essentially you have to replace s by minus I times Sc and think of Sc as a real variable. So when you do that, ds upon s will not change. There is going to be an s square which will pick up an I factor, and that will change the sign of this. So you will get 1 upon 16 pi square with the change sign 0 to infinity, and again use the same s with the understanding that we have done this rotation, e to the minus m square s. So this is nicely convergent. Here when you flip s to I times s, I factors will go away because the overall I factors will cancel out, but sine will become sin h and cos will become cos h. The sin h will become sine and sine will become sin h. So this is going to give you, now it is also probably, okay, I'll still stick with E because you want to know what came from electric field and what came from magnetic field. Sine QE, yes, this is the first factor. Then I have a QB, yes, upon sin h QB. This is what the integral is. Okay? There is just one problem, and that problem gives you something remarkable, something of remarkable physical consequence. When you do this rotation, there are poles sitting here. These are the poles at n pi due to the sin h term, because sin h for imaginary values of s is going to become sine. So they are all going to blow up when QE is equal to n pi. Okay? So these poles are at locations Sn in the imaginary distance, which is at this Sn into QE is n pi. So they are at n pi upon modulus of QE. These are each of the points. Okay? Of course, with the minus sign and I factor and all that, but you know what I mean. These are the points. So you can really rotate it and make it touch the imaginary axis. What you are expected to do is to sort of do the integral like this up to near the pole, then you do this and you do it. And you keep doing it for every pole, and this is what you do. Now when you do this, there is a circle of infinitesimal radius, and when you take that infinitesimal circle goes to 0, you are going to get a straight integral, which will contribute the real value, which is like a principal value. But you are going to get contributions on this semicircle, which will turn out to be imaginary. That is how what looks like a manifestly real integral here actually picks up the imaginary. Okay? So let us do what those quantities are. So what we are interested in is to compute this integral here. So on that arc, you can write your S as Sn plus some radius, which is epsilon e to the I theta. Epsilon is this radius and theta is this angle. Okay? So I am just going to take those contributions. Those contributions are given by the imaginary part contribution. So they are going to be given by 1 upon 16 pi square The integral now is on theta, and theta goes from okay. The correct way to define the theta is from here, because you want to have the right angled rotation around a pole. So the theta goes from pi to 0 on the integral. Okay. Then you have ds upon s cube. Anything which is not going to blow up or create problems for you, you can just replace by your Sn, because we are just evaluating on that. So your ds is going to give you I epsilon e to the I theta dt. This is the integral we are performing. From this ds, when the angle is changing, this is going to be a constant, and this is what is going to vary, and that gives you I epsilon e to the I theta d theta. Then let us take one of the, because this is going to again go for a ride. This quantity is some finite number, because this is not giving you any poles. So I might as well call this quantity as some Fn. Or let me write it down. This is mod QB Sn divided by sin h QB Sn. And in fact, if magnetic field is 0, even then it is fine. This will just become unity. Okay, the electric field is going to give all the factors you need. So let us look at this object and take this s and this s cubed out to give you an Sn square. Okay. Then you have a mod QE. Let us keep this here. So I have taken care of this, taken care of this, taken care of this. Then I have a e to the minus m square Sn. That comes from this. So the only term I need to look at is this, because this is going to blow up in my face if I just take the pole. So near the pole, I do a Taylor series expansion of that. Okay. So this function vanishes at that pole. So the Taylor series expansion will be the first derivative times the shift. So the first derivative there is going to be cosine of Sn, cos evaluated at Sn. We are differentiating with respect to S, so there is going to be a QE contribution from this. That QE just cancels with this. So that goes. Then times the shift. Shift is epsilon e to the I theta. Right? Now what is cos Sn? It is evaluated at some n pi, so it is minus 1 to the power n. And let us look at the rest of the expression. Epsilon e to the I theta cancels with this epsilon e to the I theta. Then all that remains is an integral over this, which will give me a minus pi. So that minus sign just makes this n plus 1, and you pick up a pi. This is what you have. So there is a nice I sitting here, which makes it imaginary. So I can write down immediately the imaginary part of L effective from this. That is given by rest of the expressions evaluated at every pole. So I have to sum in the denominator. So I will have q square e square upon pi square, that makes it pi cube, and an n square here. This Sn has a n pi upon modulus of QE, and it is to be summed over all n from 1 to infinity. Okay, then there is a minus 1 to the power n plus 1. It doesn't matter whether it's in the denominator or numerator, multiplied by this factor from magnetic field, which is QB Sn divided by sin h QB Sn. This is the answer. This is the imaginary part of LF. This result goes under the name Schwinger effect. And what does it tell you? First thing it tells you is that you have an imaginary part of the L effective. So if I go to this whole calculation and I interpret this e to the I d4x L effective as a vacuum to vacuum transition amplitude, when I take the mode square of that, what you get is going to be the particle production due to this external electromagnetic. So if I have an electromagnetic field in the space-time, it can spontaneously produce particles out of the vacuum. And that production of the particles, the number density of particles, number of particles produced per second per unit volume, is given by this expression. Okay, except for a factor 2, because when you take the mod square, the imaginary part will come with a factor 2. So this is what it is. Now this is, unfortunately, there is no closed sum for this, even when b is equal to 0. It is 1 by n square e to the minus some n. So we don't know how to sum that, but that is irrelevant. The most important thing here is that it is dominated by an exponential here, which tells you that if you go for n more than some 3 or 4, the terms are irrelevant because it is all going to be suppressed and there are anyway higher order corrections. But it has this QE going in exponential minus in the denominator. Okay? This is crucial because it tells you that you do not have a Taylor series expansion for this function in QE. See, it is like a function e to the minus 1 by x, near x is equal to 0. I mean, for positive values of, or you think of it as e to the minus 1 by modulus of x. Okay? This quantity near x is equal to 0 has no Taylor expansion, but it's a perfectly well-defined function at x is equal to 0. The function vanishes at x is equal to 0. All the derivatives of the function vanish at x is equal to 0. In fact, that is a good counterexample to the claim that if a function and all its derivatives vanish at a point, the function should be identically 0. If you do a naively Taylor series expansion, that f at x plus a is equal to f at x plus f prime at x into a, etc., etc. And suppose all the derivatives of the function vanish at a given point a, and the function also vanishes at that given point, then the every term in the Taylor series expansion is 0. So you would have thought that the function has to be identically 0. I mean, there are enough counterexamples to this. E to the minus 1 by x square kind of functions are good counterexamples of that. That is because they simply do not possess analytic Taylor series near x is equal to 0. So the reason I did this first is because if you do QED by the standard method, which I am not going to do for lack of time, what you will be doing is a perturbation series in E square over h cross c. And it doesn't matter how many terms you sum, even if you term infinite number of terms, you will not get this effect. Okay, because this cannot be reproduced by a Taylor series in Q. Okay, so this is a very non-trivial and non-perturbative result, which tells you that, physically speaking, it tells you that if I have a constant electric field in some region of space-time, you will find that it produces particles. Now there are honest to God conceptual issues involved in it. You can give a lot of pseudo derivations of this by saying that there is some negative energy C and a positive energy things and the electric field tilts it, etc. But none of them are really satisfactory. So that is why you need a formal machinery. So where does the energy for producing these particles come from? It has to come from the source which is maintaining the constant electric field. So if I have two capacitor plates and I produce a constant electric field between them, when the electron positron or pi plus pi minus pairs are produced inside it, they will move towards the opposite poles of the parallel plate and will discharge the electric field. It will reduce the electric field. So somebody has to maintain that electric field, and he is the one who is going to do the work in order to produce this particle. Okay. So this is what happens. Now, so that is essentially all that I wanted to tell you here. And it is also obvious that if there is only magnetic field, it is not going to do anything and it is not going to produce particles. How will you get this in a Lorentz invariant and gauge invariant way? At this stage, I just kept symbols QE and QB. You should think of QB and QE as being replaced by QA and QB. What it tells you is that the B part of it is not going to produce anything. It is the A part which is going to produce anything. Therefore, you will have sign of AS here. Okay. Now AS is going to be like electric field only when A square is greater than B square, that is E square is greater than B square. So the Lorentz invariant, this is what Sanved was asking yesterday, the Lorentz invariant criterion for particle production is that it depends on square root of E square minus B square. If square root of E square minus B square is a real quantity, particles are produced. If square root of A square minus B square is not a real quantity, then particles will not be produced. Okay. So the E square greater than B square is the criterion, and that is the Lorentz invariant. Okay. Now let us go a bit further. Let us look at actually the correction to Maxwell's equations. So that is, we want to now study the real part of the effective action. How do we do that? Well, there are various ways. One is you can go back to your original expression and take the real. Then you will get e to the minus I m square s will become a cos m square s. And you have to fool around looking at how the divergence at large s has to be handled, etc., etc. So there is a slightly better method, a trick rather, is that you look at this. This is the expression which we use. This is completely real, so there is no problem with it. Except that we know there are poles sitting along the real axis. Suppose you think of it as a real integral. Then there are poles sitting at QE equals this quantity, QES is equal to n pi at Sn. And we know what they do. You go around the poles in semicircles, and those semicircles are going to contribute for you these results, right? So if you just ignore those semicircles, then this is going to give you the correct result. It's as simple as that. So the real part would be treated as just this quantity, with the understanding that we are not going to worry about the poles on this. Okay, fine. Now let us see what that gives. Here, something very interesting happens. Let us look at the divergent structure of that, because after all we said that if you integrate out some fast mode, the resulting theory need to be renormalized, etc., etc. Right? So where are the divergent things? If you look at it carefully, you will find that first of all, even when E and B are 0, there is no electric and magnetic field, it is still divergent because there is a ds over s cube. But this is our old friend, we don't want to worry about that, because this is something which we noticed even in the case of scalar field. So that exists even in the absence of electric and magnetic field, so we don't care about it. So we will just subtract it out. So in order to compute the real part of it, what we will do is we will put a bracket here and I will subtract 1. So the 1 is what you will get when these two terms E and B vanishes, because in that limit this will become 1 and this will become 1. So you subtract that out so that you have thrown away a quantity which is completely independent of E and B. So it doesn't matter your Lagrangian, because you are going to vary the Lagrangian with respect to E and B to get effective equations of motion, etc. This term is independent of E and B, so you can subtract. Now the question is this finite? So in order to do that, we have to look at this object near the origin. Okay, so let us do that. So what we have there is something like, let us see, the electric field, let me call that part x. So it is x over sin h of x into y over sin y. Okay, we want to study this near the origin. So this is going to be xy. Let us look at the Taylor series expansion of sin x. That will be x plus 1 by 3 factorial x cube. If I think it is correct. And this will give you y minus 1 by 3 factorial y cube. Okay. So yeah, that's correct. So this will near the origin. I can take away an x here. This is x square. This is 6. And this x goes. This y also goes. And this gets replaced by 1, 6, and a y square. So this will be 1 minus 1 by 6 x square plus 1 by 6 y square. Okay, so this is 1 plus 1 by 6 y square minus x square. Let me make sure I got the signs right. I might have got it wrong. Okay, I think it is 1 plus it should come out as e square minus b square, which means that it should be a square minus, it seems to be getting y. Y is from e? No, y is, yeah, that is correct. Y is from e. The sign term has y in it, so it is correct. Okay, so this is going to be e square minus b square. So this is how this entire factor behaves near the origin. Now that is very interesting. That means, first of all, that if I do this quantity, this subtracted quantity is going to have a dependence which goes as y square and x square, and y and x has a QPS and a QES, therefore it goes as s square. That is bad news, because near the origin, even after I have subtracted, I get an s square. S square divided by s cubed is 1 by s, so it is still divergent at s is equal to 0. Okay? But something very beautiful is happening here. It is diverging at s is equal to 0, and it could have diverged at s is equal to 0 with a y square minus x square the whole square. Okay? Let me write this in terms of electric and magnetic field, then you will see this. This is 1 plus 1 by 6 q square s square times e square minus b square, which will of course be s square minus b square. It's all Lorentz theorem. This is what you have, right? If it has been a square or something else, I mean, of course, dimensionally it can't happen, but if it is something else, then you are sunk, you can't do anything. But because it is proportional to e square minus b square, and your original Lagrangian here is proportional to e square minus b square, we go back to the same analogy. You can reabsorb these divergences by changing that Lagrangian, by rescaling this. Okay? So this is again a sign that the theory we are dealing with is renormalized. There is only one divergence here. See, you will actually, when you do QED, you will find that there are different kinds of divergences and different kinds of renormalizations are needed. This particular non-perturbative example which I am taking is going to give you a glimpse of only one kind of divergence. And in that divergence, you are going to get a term which is proportional to e square minus b square. If it has been that you have got another term which was linear and square root of e square minus b square, you could not have handled this. Because this is the old philosophy. When you do the integral over the fast modes, you get an effective Lagrangian, and if that effective Lagrangian contains only the kind of terms which are present already in the original Lagrangian, you can reabsorb the divergence. That is exactly what we are doing. Here the original Lagrangian was almost trivial. It had no constants and it was e square minus b square. Saying it has no constants is not really true, because there is a half in front of e square minus b square, and there I could have put some alpha there by rescaling e. So there is a constant in front, and that is what we will use to reabsorb it by rescaling e and b essentially, which you can do. But there is no other divergent term is produced. Okay. So what we are going to do is the following. We will start with the original Lagrangian L naught. So the corrected Lagrangian or L Curtis, which we want to look at, will be the original Lagrangian L naught plus the effective Lagrangian which we have computed. Now we find that the effective Lagrangian which is written down there with just one subtracted is still divergent. So I am going to do the following. I am going to write this as L0 plus some LC or L divergent plus L effective minus LC. Okay. What is LC? LC is exactly what you get from just this term. So what I am going to do now is to look at the divergent part of that and write down an LC. LC will be 1 over 16 pi square integral 0 to infinity ds over s cube e to the minus m square s. This quantity, Taylor series expanded, gives me 1/6 q square s square q square into e square minus b square into s square. This is my definition of LC. Okay, so this quantity I am going to subtract from. Once I have subtracted this LC from this, what remains is this particular quantity is completely finite. It is quite a complicated expression because it has some sin h's and cos h's and all that. That is what you are after. There is a finite correction to your electromagnetic Lagrangian e square minus b square, which is computable. Okay. Then you have a divergent term, and that divergent term is something which I can write down. And we want to look at that divergent term in a minute. So just for fun, let me write down the expression for the finite term. Okay, that will be the following. So I need more space. So that Lagrangian, the lowest non-trivial order of that finite Lagrangian is Q4 by 90 h cross over MC. Now I am introducing all the factors upon MC square 7/4 E square minus B square the whole square minus E dot B the whole square. You will have the correct factors in the handout, and I think this is correct. Q by 90 and 7/4. Yeah, this is plus. Okay. As I said, this is just for fun. I mean, it's not for your exam, or you don't have to compute this or whatever. So if you just subtract that term out, then you can ask what is the next leading term. We have gone up to q square there. So the next leading finite term is q4 term. You take that q4 term and do the integral. Okay. So integral over s can be performed there, and if you compute it, you will get this. What it tells you is that you take half e square minus b square and add to it this. That will be the correction to Maxwell's equation. See, I wanted to show you at least one concrete result in a field which you are familiar with. You are all familiar with e square minus b square and how to vary e and b in order to get Maxwell's equation. Now you can go back and redo the same thing with this, and this will give you corrections to the Maxwell's equation, quantum mechanical correction to Maxwell's equation signaled by H cross, arising because the electromagnetic field is all the time coupled to scalar quanta. You could have done exactly the same analysis for electrons. You can take Dirac theory, integrate out the electron-positron fields out of the electromagnetic field. You will get very similar expression with coefficients different. Okay. Now the first thing it tells you is that it has a non-trivial structure. No one can guess this. I mean, all these coefficients, etc., etc. So it requires a computation, and it tells you there are these kind of corrections. People have tried to see whether there is an evidence for this experimentally. So the idea was to use very intense laser beams, which has very high electric field. See, the threshold for pair production, everything is set by this QE upon M. Okay, and that quantity, it turns out, most of the time is not sufficiently high. So you need a very high electric and magnetic field. And in astrophysical situations near pulsar surfaces, there seems to be situations where this does happen. But it's not like a laboratory detection. So people have tried to do this. But the results are sort of ambivalent. But this is what you get as a correction. So there isn't much else which I wanted to say about this, but if you have time and inclination, you can try varying it and see what kind of corrections to Maxwell's equations come up. But the main point to take home is that there is a algorithmic procedure by which we could compute quantum corrections to minus 1 part ref square by integrating out the scalar field, and you do get a finite result. Now let us go back to this, because that will tell us about the running of the coupling constant here in the case of Q, at least in a very simple context. So let us look at that also. So what happens here? Here you find that you have this expression for LC, which I want to write in a manner very similar to our original expression. So I am going to write it as half E square minus B square times a parameter mu. Okay, so what is the parameter mu? That is what is left here. So I have half of that taken out. So there is a 3 times 16 is 1 over 48 pi square integral 0 to infinity ds over s cube, then an s square, so that makes it as q square e to the minus m square. What is that? Okay, so let me again make sure the factors are all right. Yeah, so this is what we have. So what happens is that when I take this LC and I add to this L0, so there is a L finite, which is this quantity, plus L0 is half E square minus B square. So I am going to get half into 1 plus mu into E square minus B. Okay, so it essentially says that if our original constant, so to speak, was half, and if I had originally written down the Lagrangian with a coupling constant alpha by rescaling E by alpha times V, if there was an alpha, that alpha gets rescaled into alpha into 1 plus mu. Okay, so this is what is happening. So what we want to do in order to do this thing more formally, what we will do is to introduce physically relevant electromagnetic fields and charge. So we will take this expression here and use that to define E physical. This is the observed physical electric field and magnetic field, which we will say is equal to, or E square physical is equal to 1 plus mu times the original E square, and similarly B square physical is 1 plus mu times, you can think of it as a field renormalization because we didn't keep a constant originally there, times B square. So this is just a rescaling, so that the original Lagrangian here is back to E square minus B square in terms of physical electric field. After all, that those are the electric fields you will be measuring. But in order to compensate for this, you have to make Q square physical to be same thing with reverse, 1 plus mu to the minus 1 original Q square. This is needed because QE and QB should not change. So the finite part of the Lagrangian which we wrote down, I have wiped it out. But a finite part of the Lagrangian had QBS and QES with an integration over S. So QB and QE remain the same, and that can be now replaced by Q physical, E physical. So everything is fine. You renormalize the charge by this amount, and then your finite part is fine, and the divergences has been removed, and your background term is half E physical square minus B physical square. So we have done everything. So that is essentially the end of it. But let us just look at this a little bit more. Okay? And let us look at the nature of divergence in V. It's a little peculiar compared to what we got in the scalar field case. So here we have to again do the same kind of analysis. I have to evaluate this integral, and this integral is divergent at the lower limit, so I have to put a cutoff. So let me do integral lambda to infinity ds over s e to the minus m square. So this is again first function into integral of the second, which is log s, minus integral of derivative of the first function that is minus m square derivative of the first function into integral of the second, which is log s dx. This is what we have. Okay. Now we are supposed to take the limit lambda and infinity here. So this will give me, at infinity everything vanishes. At lambda, finally we are going to set lambda equals 0. So by the same philosophy we won't touch that. So I get a minus log lambda. Then I get there plus m square integral. This is finite, so I can put 0 here, 0 to infinity, e to the minus m square s log s dx. Okay, we play the same game again. M square s I will call x, so this becomes dx. This is x. So this is x by m square. This is what we have. So there are two terms. One is with log x and one is with minus log m square. Minus log m square, the integral is unity. So let me write that down first. So minus log lambda minus log m square. Then I have an integral dx log x gamma of x. This is the Euler constant, so that is just a constant. We just call it c. This is what we get. Now what do we do? It's slightly different compared to the previous case because the cutoff has to be introduced by hand. Okay. Normally I'm going to assert that I'm going to deal with a limit when lambda is going to 0. So this is going to go to negative infinity, this is going to diverge. If it is diverging, then there is no point in keeping anything finite. So I can just throw them away. But then I run into the standard problem that you don't want a log of lambda with no energy scale associated with it. So you want to divide it by some quantity. So we again play the dimensional game. Your lambda, which was introduced, has the dimensions of S, which has dimensions of 1 upon energy square, because m square s is dimensionless. So S has the dimensions of energy square, so this is like E infinity square. Okay? So you put that E infinity square here. And you can make this plus and put a E infinity square on top. minus log m square. Now both of them has energy scales in it. So what you do is you introduce another energy scale, let me call this E square, and you can put the same energy scale here. Nothing has changed because in the logarithm I have put here and they subtract it out. Now I can say that this is going to be divergent while these are finite and throw away these two terms. Okay? So the answer which I get after I do all this is that this divergent factor is going to be this. So this is going to be q square over 48 pi square log some E infinity square upon E square. This is what you get. What does this mean? In order to understand what it means, let us go back to this relation and write it as 1 upon q physical square is equal to 1 upon q square into 1 plus mu. And 1 plus mu is what we have here. 1 plus mu is 1 plus q square upon 48 pi square log E infinity square upon E square. We interpret this exactly the way we interpreted before. We think of this q physical square as the coupling constant at an energy scale E. Okay? So this of course you can be simplified a little bit. So you get 1 upon q square here plus 1 upon 48 pi square log E infinity square upon E square. Okay? Let me just make sure the signs etc. are correct. Yeah, that's correct. Therefore, if I look at the charges defined at two different energies, so it is q square physical. Now I will just call it, let us say, E prime minus 1 upon q square evaluated at E. When I do that, I will have 1 upon 48 pi square. When I do it for E prime will be in the denominator, and then I am going to subtract the other quantity, so that will go to the numerator. So it is equal to log E square upon E prime square. It's a bit of a bad notation. E is also electric field, but you know what I mean. Okay, so this is what you have. So if you look at any one of them, so this let us take this E and then log E square. So I can take them to the same side. So just as we did in the case of scalar field theory, 1 by q square at E plus 1 upon 48 pi square log E square remains a constant. As you change this also, I want to make sure the signs are correct. Yeah. What does this mean? So now that we have got the maths out of the way, let us go back to the physics. So you had a divergent term here which you regularized and you got this. Once again, you can think of this exactly in the same way we did in the scalar field. You can think of this, roughly speaking, arising because you have integrated out the cosmos between energy scales E and E infinity. Okay? So your E is like your renormalization point, and you are going, somebody is going to do some scattering experiment and tell you what is the coupling constant of the electronic charge when you do scattering experiment at some energy E. Okay? That will involve, when we do formal computation, a divergent term which is regulated by an upper cut of E infinity. So this is the picture which we had even before. You have an E infinity then you have an E, and you can have a E prime here. So what you are doing is that when you are integrating out all these degrees of freedom, you end up getting a charge at low energies, which depends on these two. And that is a bit meaningless because we have to send E infinity to infinity at some stage, which is what we do like. But you don't have to worry about it, because suppose somebody gives you this E and Q at E. Then you say, suppose I am working with a E prime, that is I rescale and do up to this, what Q should I use? That answer is perfectly finite, and that is given by this relation. If I know E, Q of E at some E, if you want to compute Q at E prime and any other E prime, just use this principle. Okay? And that gives you the fact that this is the way the term is going to grow. And you can again write down what is the beta function of the theory. That is, you can write down dq divided by E dE, and you will find that there is a particular value which depends on 1/48 pi square, etc. This coefficient depends on our original calculation where we have integrated out the scalar degrees of freedom. If you go and integrate out the electronic degrees of freedom, you will pick up a different coefficient. So actually how the charge Q is going to run is going to depend on how many degrees of freedom it is coupled to. Okay? In that sense, it contains the information about all other degrees of freedom, or it depends on the model which you are using. So if you have a theory which has 13 scalar charges and 3 fermionic charges, then it will have a coefficient which is different from if your theory has something else. Now if some experimental is going to tell you what is the beta function of the theory, that fixes for you these numbers. So in that sense, it is a very, very observationally direct, non-abstract result, even though we have been fooling around all along with divergent terms and the like. Okay. Now this is not the whole story, and in fact I have sort of taken some liberties in presenting it in this way, but it contains the essence of this. This particular running of the electromagnetic coupling constant and the beta function which we have derived is exact. Even when you do QED with the perturbation theory and all that sort of stuff, this is the result which you will get, except for the numerical factor which depends on what degrees you are throwing off. But this is not the whole story in the sense that, for example, we haven't talked about a mass renormalization atom. There are parameters like mass in addition to the charge which appears in the theory, and when you do this all quite formally, it is not just the charge which gets renormalized, but all the parameters in the theory Lagrangian gets renormalized. But we have only looked at a glimpse of it, but that is quite adequate for this course. Okay, so I think that is all which I wanted to say about this. And next week we will do Feynman diagrams for the lambda 5-4 theory. It actually is much simpler than it is made out to be. So we just need 3 lectures. So I hope to conclude by next week. And next week there is a holiday. I think Thursday is a holiday. Okay.
Fridays.
Yeah, but Friday I don't care because I am not talking. Okay, but Thursday is a holiday, some Mahavir Jayanti or something. But I would like to take class on Thursday. Okay, so